This is Mark Liberman, and I'm presenting on benchmarking for long-term research management, the Common Task Method. Over the course of half a century, DARPA's Human Language Technology program created capabilities like speech recognition, machine translation, and text understanding, turning them from fantasies to everyday practical fact. This sustained success was based on the development of the Common Task Method, which allowed decades of incremental progress in advance of commercial viability. I'll describe the origin and sometimes counterintuitive progress of this method, distinguish it from other uses of benchmarking, and speculate about its future. So what is a benchmark? Well, according to the Oxford English Dictionary, a benchmark is originally a fixed point, especially a cut or mark in a wall or building, used by a surveyor as a reference in measuring elevations. Typically, such a mark takes the form of a horizontal groove cut in a surface into which the upper surface of an angle iron would once have been inserted, forming a level surface or bench to support a leveling staff. Figuratively, the dictionary goes on to tell us, in extended use, a benchmark is a point of reference, especially one from which measurements can be made, something that serves as a standard by which other similar things may be measured or evaluated, especially a standardized problem or test used for evaluation or comparison. So what are these figurative benchmarks used for? Well, selling stuff. Our widget is the best. Look at this benchmark. Buying stuff. Which widget is the best choice for this task? What should we get? Process planning. How much of X do we actually need to do this? Process management. How much X are we using to do this? Education, which students have learned what, and so on and so on. As diverse as they are, those benchmarks all aim at near-term action, buying, selling, planning, evaluation in an ongoing practical situation. A different kind of benchmarking played a crucial role in the history of human language technology. Now, these days, human language technology is more and more widely used, and there are 4 secrets to its success. Obviously, better algorithms, cheap, fast digital hardware, ubiquitous digital networking, and a research management technique that was developed in the 1980s and has been applied increasingly widely since then. The first 3 of those driving forces are obvious, but the third one involves some semi-obscure intellectual history, which is worth knowing about. The foundation was a fairly long series of human language technology failures. Especially in the 60s and 70s, there were many projects that were focused on machine translation, natural language interaction with databases, speech recognition, and speech synthesis. These were based on human-coded rules or constraints, and they generally worked to some extent, but they were limited in scope. They were brittle under even modest changes in context. They were expensive to create and port, and they were generally disappointing in performance anyhow. Now, many influential people concluded that these endeavors were hopeless, and a leader for pushing this narrative was John Pierce. He had supervised the team that built the first transistor. He oversaw development of the first communications satellite, so his opinion carried considerable weight. This is John Pierce. This is what engineers looked like in the 1960s. Pierce was skeptical because there was a long history of failures, not to say total nonsense. Already in 1913, Efficiency magazine had a little article about an alleged voice-operated typewriter developed by John B. Flowers of Brooklyn, New York. And the cover of the Electrical Experimenter in 1916 showed his device. 50 years after that, there was promise after promise and failure after failure. And in 1969, John Pierce, in an article in the Journal of the Acoustical Society of America called Whither Speech Recognition, wrote that a general phonetic typewriter is simply impossible unless the typewriter has an intelligence and a knowledge of language comparable to those of a native speaker of English. Most recognizers, by which he means researchers working on recognition, behave not like scientists, but like mad inventors or untrustworthy engineers. The typical recognizer gets it into his head that he can solve the problem. The basis for this is either individual inspiration, the mad inventor source of knowledge, or acceptance of untested rules, schemes, or information, the untrustworthy engineer approach. The typical recognizer builds or programs an elaborate system that either does very little or flops in an obscure way. A lot of money and time are spent. No simple, clear, sure knowledge is gained. The work has been an experience, not an experiment. When he goes on to tell us what he really thinks, we are safe in asserting that speech recognition is attractive to money. The attraction is perhaps similar to the attraction of schemes for turning water into gasoline, extracting gold from the sea, curing cancer, or going to the moon. One doesn't attract thoughtlessly given dollars by means of schemes for cutting the cost of soap by 10%. To sell suckers, one uses deceit and offers glamour. It is clear that glamour and any deceit in the field of speech recognition blind the takers of funds as much as they blind the givers of funds. Thus, we may pity workers whom we cannot respect. Now, the fallout from these blasts was first, well, all right, there's this new idea, artificial intelligence, and the DARPA Speech Understanding Research Project in the early 70s wanted, among other things, to use classical AI to try to, quote, understand what is being said with something of the facility of a native speaker. But this program was viewed as a failure and funding was cut off after 3 years. And the second idea was give up. So for more than a decade, there was essentially no US research funding for machine technology, for machine translation or automatic speech recognition. John Pierce was not the only person who had a jaundiced view of R&D investment in human language technology. By the 1980s, many informed American research managers were equally skeptical. But at the same time, there were many people who believed that HLT was needed and in principle was feasible. So in 1985, DARPA began to explore restarting HLT support. Some smart program managers had a new idea. They designed a program that would protect against glamour and deceit because it would have a well-defined objective evaluation metric that would be applied by a neutral agent, National Institute of Standards and Technologies, on shared data sets. And it would ensure that simple, clear, sure knowledge is gained because participants would be required to reveal their methods to the sponsor and to one another at the time that the evaluation results were presented. This requires published data and well-defined metrics, as Dave Pallett pointed out in a 1985 article. And it led to the development of a common task structure, which had a detailed task definition and evaluation plan that would be developed in consultation with researchers and would be published as the first step in the project. There would be automatic evaluation software written and maintained by NIST and published also at the start of the project. Shared data, training and development test data that would be published at the start of the project. Eval test data would be withheld for periodic public evaluations. Now, not everybody liked it. Many Peirceans were still skeptical. You can't turn water into gasoline no matter what you measure, is a phrase that I heard in those days. Many researchers were disgruntled. It's like being in first grade again. You're told exactly what to do and then you're tested over and over. But it worked. Why did it work? Well, the obvious reason was that it allowed funding to start because the projects were perceived as glamour and deceit proof, and it allowed funding to continue because the funders could measure progress over time. A less obvious reason was that it allowed project internal hill climbing because the evaluation metrics were automatic, the evaluation code was public. This obvious way of working was a new idea to many people, and researchers who had objected to being tested twice a year began testing themselves every hour, or at least as often as they could rerun their system. Even less obvious reason it worked is that it created a culture because researchers shared methods and results on shared data with a common metric, and participation in this culture became so valuable that many research groups joined without funding. What else it did was to create a positive feedback loop, because when everyone's program has to interpret the same ambiguous evidence, ambiguity resolution becomes a sort of gambling game, which rewards the use of statistical methods, which after all were originally developed to model gambling and led to the flowering of machine learning. Given the nature of speech and language, statistical methods also need the largest possible training set, which reinforces the value of shared data. And iterated train and test cycles on this gambling game are probably literally addictive. I think people get a dopamine squirt from it. They create simple, clear, sure knowledge, motivating participation in the common task culture. And so this method has become the standard research paradigm in experimental computational science. It involves, as I said, published training and testing data, well-defined evaluation metrics, techniques to avoid overfitting, and it can apply to any sort of algorithmic analysis of the natural world. And over the past decades, variants of this method have been applied to many problems: machine translation, speaker identification, language identification, parsing, sense disambiguation, information retrieval, information extraction, summarization, question answering, optical character recognition, sentiment analysis, and even things that are not really HLT, like image analysis, video analysis, and so on. The general experience is that error rates decline by a fixed percentage each year to an asymptote that depends on task and data quality. Progress usually comes from many small improvements. Improvements by as much as 1% is a reason to celebrate. Shared data plays a crucial role and is often reused in unexpected ways. And for the most part, glamour and deceit have been avoided. Versions of this method are now routinely used outside of sponsored projects by both academic and industrial researchers, and challenges in this spirit are routinely created by technical societies and ad hoc groups. I want to note in passing that there's some very important areas that are lagging decades behind, both in technology and in methodology. These include clinical applications, educational applications, and legal applications. And a cultural change in those fields is way overdue. As AI and human language technology have advanced, benchmarking has begun to assume a more traditional role in assessing and comparing practical systems, because we now have practical systems. But it's important to recognize that benchmarking of practical technologies is different from benchmarking for decade-scale research management. In fact, in some ways, they're opposite to one another. For decade-scale development, we need efficient metrics that are aimed in the general direction of distant goals. Efficient means that you can try a lot of things quickly, where quickness is, of course, relevant to the speed of the computational systems at your disposal. General direction means that better results are probably progress, even if the metric is too crude to validate actual applications, and even if there are, in fact, no applications. Distant goals means that we're not working on specific applications, though, of course, demo systems are always in order. Successful metrics of this kind can be very crude. For example, word error rate, as if all mistaken words are equally important, which they obviously aren't. The blue translation metric, which pretends that word order doesn't matter in translation, it's just a matter of comparing bags of words. It's easy to create examples where these metrics fail arbitrarily badly, but they point in the right direction, at least at certain stages of development. Now, near-term technology evaluation needs a different kind of metrics that are aimed at specific real applications, or at least specific classes of real applications. Their cost function has to be appropriate for the application. For example, word error rate and word-based metrics of all kinds now need to weight mistakes according to the effect on downstream decisions, or indeed, perhaps we need to evaluate the effectiveness of the downstream decisions on their own terms. And these decisions might be human or automatic. Accurate evaluation of this kind is task-specific, time-consuming, and in general expensive. There's also a kind of intermediate case where we want to compare different algorithms or different parameter settings for the same algorithm on a general class of now practical technologies. And except for the practical part, this is really the same as the historical common task method, but tuning a working algorithm using a long-established metric, or trying a small variant on a working algorithm, is quite different socially, intellectually, and in other ways from devising a new metric to help us explore a space of solutions for a problem that no one now knows how to solve. we need to do a better job of benchmarking human language technology research and development at all scales of time and all levels of task specificity. But decade scale technology development requires a special kind of creativity in devising, evolving, and applying metrics. And funders, managers, and researchers all have a role to play in that process. Thank you for your attention.